Welcome to lesson 2.1 in the circuit or electronics 2 class. Again, as I said previously, I'm going to try not to refer to this lecture series by the class name, by the specific class name, because it changes so much. So we'll just call this, it's electronics 2, and it's the first real lesson, so we'll call it lesson 2.1. And today we're going to be talking about amplifiers. We're going to be talking about amplifiers generally, and then op amps, and we're going to talk about models for these and the ideal model. So let's just look at the basic voltage amplifier. So the basic voltage amplifier has, internally, it has some input. Well, first of all, it's a two-port network, 2 ports in, 2 ports out. Internally, it has some input resistance, Ri. It has an output voltage, which is, as this is a voltage amplifier, that voltage is some gain term, which is that AOC, times the input voltage. The input voltage being the voltage across these input terminals. And then it's got also some output resistance. And I'm kind of cluttering this up. But these amplifiers they don't just exist by themselves, right? Well, they can exist by themselves, but they're usually connected to something at their inputs and outputs. So 2-port networks, you got 2 ports out, connected to 2 ports in, 2 ports out, connected to 2 ports in, and so on and so forth. And so in this case, we model the source and the load as well. So we're looking not only at the amplifier, but also the source and the load. And the first thing to notice is that the output voltage, although ideally your output voltage of the amplifier would be this term here, because we have this non-ideal internal resistance, the actual output voltage is not going to be the voltage of this voltage amplifier internal to the device. It's going to be some divided portion of that. So basically, to find the output voltage, we have to do a little voltage divider, and that's what's done here. So it is the internal voltage, which is the input times that gain, that AOC, times this voltage divide, times this ratio of resistances. And that, again, that is just the voltage divider formula. And we have something similar on the input. So on the input, ideally, the input to the amplifier would simply be this supply voltage, which is connected to it. But our system, our network that's connected to the input of our voltage amplifier, undoubtedly, if it exists in this universe, it has some non-ideal source resistance. So it's going to have some resistance in series with that input voltage signal. And as a result, the voltage at the input of the amplifier is not this VS. It's actually a voltage divider formed by these 2 resistors here. So it's going to be the voltage across Ri, the input resistance. So again, we have another voltage divider. So basically, the internal resistance of the voltage amplifier at both its input and its output, coupled with the resistance of the load or the resistance of the input, produces these kind of voltage dividers at both ends of our voltage amplifier. And combining these 2 equations together, we get, plugging this in here, we get this equation for the overall gain of this amplifier system. So the input taking into account non-ideal source, the output taking into account non-ideal load, we have this, the gain of our system is not simply A, it would be nice if it were. The gain of our system is A, but then attenuated by these voltage divider ratios at both the input and the output. Okay, and so let's think about that. So we just sort of derived the equation here. We talked about how we derived the equation, but let's start looking at the math of this equation. So if we look at the math of this equation, and keeping in mind, we want our overall gain to be that gain of the amplifier, the internal gain of the amplifier. That's what ideally, that's what our overall gain of our system would be. Well, mathematically, what does it take to make that true? Well, you'll notice, if Rs is 0, then this expression becomes R input divided by R input, which is 1. So if Rs is 0, that cleans up the input side. So if the source resistance is 0, then the input voltage will be the actual true source voltage. And on the output side, if RO is 0, then this just becomes the ratio RL over RL, which is just 1. So here, ideally, if the output resistance of our amplifier is 0, that also will clean up that output. So if our ideal gain is AOC, that's just the internal gain of the amplifier. It's usually called the open circuit gain. And if RS is 0 and RO is 0, so basically if this one is 0 and this one is 0, then in fact, our overall gain of our system will be AOC. But that's, again, that would be great, but that's not always true. So assuming that's not true, what can we do to mitigate that? So assuming that RS is non-zero and RO is non-zero, what about this equation will minimize the impact of that? Well, another thing, if you note mathematically, if RL is very big and RI is very big, then it's going to dominate these two terms here, right? I mean, think about it. If RI is a billion, then this expression here, and I'm going to clean it up, right? So if RI is really, really, really big, a billion is a big thing for me, I guess. If that's really big, then let's say RS is 1,000. Well, if RS is 1,000, but RI is a billion, we get a billion divided by a billion plus 1,000, who cares, right? So basically, if RI is very big, if that input resistance to our amplifier is very, very, very big, then the non-zero resistance of our source isn't as big of a deal. And similarly, on the other side of this expression, let's say RL is very, very, very big, like a billion, right? If RL is really big, then RO can be a little bit bigger without it having a big overall impact. And so basically, assuming we can't have 0 for our supply resistance or our output resistance of our amplifier, we can still minimize the impact of them being non-zero by having a very big input resistance and a very big load resistance. Okay. Now let's look at the current amplifier. The analysis of the current amplifier is very similar, right? I mean, the only difference is when we have a current source, we sort of use this Norton model for the source. And looking at this Norton model, I'm not going to fully go through the math like I did in the last one, but let's just think about this. If we have a current source and we want all of this input current to flow into our current amplifier, what would it take? It would take this resistance to be very, very, very big. So basically, when it comes to current sources, we want the supply resistance to be very large. If the supply resistance is very large, then essentially you have a current divider here and here. If the supply resistance is very large, you will have almost all of the current actually flowing into your input of your amplifier. And conversely, you want this input resistance of the amplifier to be very, very, very low. So when you have a current input ideally has a high impedance, high resistance source and a low resistance load. And that's sometimes a little strange for students to think about, okay, we have a signal and we want to have a 0 ohm load. We want to have that signal going into a 0 ohm load. Students, that usually it's a little weird because it's, so basically you want a short circuit. You want to have that input connected to a short circuit. Well, yeah, you do in the case of current when a current's your signal, because currents love short circuits. All right, if you have 20 milliamps, 20 milliamps would love to flow through a short circuit. It takes 0 volts for 20 milliamps to flow through a short circuit. But if you have a very high resistance, say you have 20 milliamps flowing into 10 kiloohms. Well, if you have 20 milliamps flowing into 10 kiloohms, it's going to take 200 volts in order to achieve that 20 let me see if I'm doing that right. 20 milliamps, 10 kiloohms. Yeah, it's going to take 200 volts. So basically, that current supply is going to have to build up 200 volts to maintain that current. So currents are the opposite of voltages, or they're complementary to voltages. So if your mindset is voltage supplies and your mindset is We always want very resistive loads. That's not true with currents. With voltages, the mindset is we want low resistance supplies, high resistance loads. The opposite is true with current sources. You want high resistance sources, low resistance loads. So that's what we see here, right? Again, it's when you're dealing with a current source, the source resistance, you want that to be as big as possible so no current flows internal to the source, regardless of what load you connect it to. And for your load, you want that load resistance to be very small so that all the current flows to your load regardless of what the source input internal resistance is. Okay, and then same thing is true on the other side here. The smaller this load resistance is, the more of the current will flow to the actual load. And conversely, the bigger the internal resistance here is, the less of this amplified current is going to be burned internally in our amplifier. So just to clarify, we are now, the current amplifier is the complement to the voltage amplifier. We want very low input impedances and very high output impedances, which means that looking at this transfer equation, ideally we would have our I be 0, that's this. Ideally that would be a 0 ohm input resistance. For the same reason in the previous example, we wanted our supply to have a 0 ohm supply resistance in the voltage case. Now in the current case, we want our input to have 0. Mathematically, the equation looks the same. It's just flipping the two sets of values. And also we want our load to be 0. So we want these quantities to be 0, but we can't always achieve that. So that's not always achievable. We don't get to make things 0 in the real world. So if those can't be 0, how do we mitigate it? Well, we want that ratio to be, we want those values to be as big as possible. We want R out to be as big as possible and RS to be as big as possible. So assuming we can't have 0 ohms loads, we want to have very high resistance sources, very high resistance sources. Okay, and that's the, I think current signals tend to throw students off more than any other. Currents are often used, or at least they used to be often used. 4 to 20 milliamp signals used to be a very common industrial signal. They still are fairly common. But one thing that throws students off when they're working with a signal that is, say, like a 4 to 20 milliamp signal is sometimes they inherently want to have it go into a high resistance load, a high impedance load. And you don't want that. You want a low impedance load for a current signal. Looking at the general case, so we just covered the voltage amplifier and the current amplifier. Just jumping ahead a little bit, op amps, nearly all op amps that you buy nowadays are actually voltage amplifiers. So you might say, well, why do we care about the current amplifiers? Why do we care about these other, why do we care about transconductance and transresistance amplifiers? The reason is because even though the actual op amp itself is very likely to be a voltage amplifier, by changing the configuration of the op amp, we can make it behave as a current amplifier or a transconductance amplifier or a transresistance amplifier. Op amps are extremely versatile in that way. They can be converted into almost any amplifier topology. And so these amplifier topology features remain very important. So just to quickly summarize, a voltage amplifier, input volts, output volts. Ideally, we have infinite resistance on the input of the amplifier, 0 resistance on the output of the amplifier. The current amplifier, input current, output current. Ideally, the input is 0 ohms resistance and the output is infinite resistance. Transconductance amplifier. This is an amplifier that has an input which is a voltage and an output which is a current. The input is a voltage and the output is a current. Then you want an infinite ohm input, because your input is a voltage. The voltage wants to feel that infinity ohms. It's easy for a voltage to feel infinity ohms. And the output is a current, so you want that to be also infinity ohms of output resistance, because you want all of that current to flow to the load, not internally. So that is infinite resistance or impedance. I kind of use the terms interchangeably in this class. When you learn circuits, you learn the difference between resistance and impedance is a special case that takes into account sort of takes into account reactive or takes into account the relationship between voltage and current due to devices like capacitors and inductors. So it's the complex quantity of the complex quantity equivalent of resistance. So but I use the terms interchangeably. Resistance is a type of impedance. Impedance is a more complicated version of resistance, but just be aware that's what I do. I not only do I confuse them in lectures, apparently I confuse them as I'm describing them in lectures. So, and then a transresistance amplifier. This transresistance amplifier has an input of current and an output of voltage. So for that current input, that current wants to see 0 ohms, and for that voltage output, we don't want to have any resistance on that output voltage because we don't want to produce a voltage divider to our output. So, okay, that's sort of the general overview of amplifiers. You know, some of this, you've probably seen some of this before. Maybe you've seen these models, but we kind of, in this class, we're setting the table. We're setting the table for non-ideal effects. So to do that, we have to start off by saying, you know, here's the way amplifiers are actually structured. Here's the stuff that's not great about them. They have input resistance that's non-zero or non-infinite. They have output resistance that's non-zero or non-infinite. So let's consider the op-amp model. An op-amp model is a special type of two-terminal amplifier. The only real difference between the op-amp model and the generic voltage amplifier model that we just showed is the op-amp model is just implicitly this gain term should be very high for an op-amp. So, you know, a normal amplifier, whatever, the gain could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The idea behind an op-amp is basically just it's a voltage amplifier that has a very high gain. Very high, not really clearly defined. And you'll see in this class, they sort of work even when the gain is not very high, just not great. Okay, so one thing to note is the power supplies of these op-amps are generally not shown for clarity. Power supplies for op-amps are very important, especially when it comes to knowing, you know, clipping, when it comes to knowing rail-to-rail performance, when it comes to decoupling those supplies for stability. These are important, supplies are important, but we don't show them. We don't want to clutter our circuit drawing usually, so we just leave them off. One thing to note, so in this case, we show the output voltage as a single terminal and the input as 2 terminals. So what's happening here is the input of an op-amp is typically described as double-ended or differential, meaning that both of those terminals can have a voltage that is independently referenced relative to the ground reference for our amplifier. And the output, though, is usually considered single-ended for an op-amp, meaning that the output is a voltage that is referenced to the ground reference, internal to the amplifier. So, so we have 1 terminal for the out, 2 terminals for the in, even though it's really just an input voltage and output voltage. Typically, the op-amp model is usually by having 2 terminals as the input, it's implicitly a differential input, a double-ended input, versus the output, which is only referenced to the ground. Okay, and a couple other parameters here. RD is differential input resistance. RO in this case is the output resistance. And the output resistance, be very careful with that. That's the output internal to the op-amp. So, and then little a is the voltage gain. Be very careful with A's in this class because we have little a, we have big A, we have a couple of big A's, and we have alpha. So we have little alpha, big A's, and little A's, and they mean different things. So in this case, the little a is the open loop voltage gain of our amplifier here. All of these parameters are called open loop parameters. The book that we use differentiates open loop with closed loop with capital and lowercase. So when you see these lowercase letters, typically that means we're talking about the open loop parameters. So little d, little o, little a, open loop parameters. Open loop meaning these are terms that are derived just from the amplifier definition itself, not from the feedback network that you connect to the amplifier. Okay, another term. So a lot of this class is just throwing names out there and making sure we're clear on what they mean. So VD in this case is a differential input voltage. So you might say, well, it's a capital D. So does that mean it's a closed loop term? No. Yeah, so VD is just the differential input voltage. It just refers to the voltage difference between VN and VP. So looking at this amplifier, fairly straightforward. What's the differential voltage? It's VP minus VN, of course. The difference between the two inputs is going to be that input differential. And what's the output going to be? Well, again, it's fairly straightforward. It's going to be the gain, going to be the open loop gain term times the VD, that input differential. And so again, substituting that for that, we get this expression. And if we want to write this, then another way to write the input differential based on the output voltage and that gain term is like this. So quite often when we're solving these circuits, we will solve for the output voltage and then say, okay, if that was the output voltage, then what did my input differential have to be to make that true? And a lot of times we solve it in that direction because as a result of the very large gain of these amplifiers, the output voltage typically is more substantial than the input differential voltage. So a lot of times we can start by making a simplifying assumption about the input differential voltage and then solve for the output voltage and then work backwards and say, okay, what was the input differential voltage for real? What was it actually? And see whether or not that matters. Or sometimes we just solve it the complex way. So the ideal op-amp model. So this was the op-amp model and the op-amp parameters. Technically, you could take this model and basically do this entire class. All this class really needs is this. The problem is you'll find connecting this model to a complex circuit can very quickly create very complex equations. So what is an ideal op-amp? An ideal op-amp has a gain of infinity. An ideal op-amp has an input RD, input resistance that is infinite, and an output resistance that is 0. So again, these are the ideal effects for a voltage amplifier in an ideal op-amp model. And also, we have this assumption with an ideal op-amp model that there is no current flowing into the P and N terminals. So no current flowing into the terminals of the op-amp. Now, I always like to say, how many of these, whenever we talk about what's ideal, what's not ideal, I always like to think, what of these are actually good in the real world? I'm jumping ahead to the real world. What of these parameters are pretty good assumptions? Well, the gain being infinite is not a great assumption. And actually, that's probably one of the biggest areas where where that assumption being bad is going to skew the results of the circuit that we create. And so the actual gain of op-amps, some op-amps have very high gain. So the classic OP77 op-amp typically has a gain of over 1 million. But an LM741 you're typically talking more like 60,000 to 100,000 or so. So it's different. And some op-amps, especially high-speed op-amps, sometimes the gain will only be sometimes the gain will be less than 1,000 for those types. Sometimes you have a trade-off of, internally in these devices, having very large gain typically means you have to have several cascaded amplifiers. So you have one amplifier feeding another amplifier, feeding another amplifier. There's a cost to that. There's a delay cost to that. There's a phase shift cost to that. So sometimes you have to kind of make trade-offs. Sometimes you can't just get unlimited gain without paying a price when it comes to speed and power consumption and things like that. Everything has a cost. So the gain being infinite is not a great assumption. But as we'll see in this lecture even, sometimes it's close enough, right? Close only counts in horseshoes and hand grenades and op-amps. So RD being infinite, this is oddly enough sometimes a very good assumption. So RD being infinite, some op-amps, the input stage of the op-amp is the gate of a MOSFET or similar. Right? Sometimes it's an oxide gate. So sometimes the input terminal is a metal gate, a oxide insulator behind it. So sometimes the resistance of these is extremely high. We're talking some op amps have tens or hundreds of gigaohms of input resistance. So not always. Again, sometimes to be faster, they'll use a BJT or something. So, older op amp designs use BJTs. You're not going to get, no current flow into those. That's not the same as an oxide gate. So some of those will have an input resistance that can, be anywhere from 10, usually it's 100,000 ohms or more, but it varies. But there are op amps, many op amps, where this input resistance being infinite is a very good assumption. And then the output resistance being 0, no way. No way. So this is a very bad assumption normally. So normally the output resistance of op amps, a low output resistance op amp would have an output resistance of under 100 ohms. But, 50 would be, 50 ohms of output resistance would be fantastically low for an op amp. 741 is, I think, about 75 to 100 ohms output resistance. So what does that mean for op amps? A lot of times that output resistance usually only comes into play when you're trying to drive large currents out of the op amp. So a lot of times you can design circuits that they don't really require that much current draw, and as a result, that output resistance doesn't have a huge impact, but we still have to pay attention to it. We still have to quantify it. We still have to take it into consideration. What about the current flow being 0? What about this assumption? Well, that's kind of tied to this a little bit. It's not entirely tied to that, but right. So technically, the resistance shows, yeah. Well, but usually that's again pretty good for most op amps. The current flowing in being 0 is pretty good. When it becomes a problem, though, sometimes people try to push the limits of what they do with op amps. So if you have an op amp and you have an input which is, a tree, like I talked about in the last video, and that tree has a resistance of 1 gigohm, well, now you got to be careful. Now even a small, going back to our equations, if your source resistance is extremely high, if this is a tree, and that RS is a million, well then, these have got to be astronomically big then to make that not have a big impact on your circuit. So something to consider. Okay, so now let's jump into it. So now we've said here's our amplifier model, here's our op amp model. Now let's actually see what happens with these op amps. And we're going to start with the non-inverting amplifier. So this lecture series assumes you've already had a background on ideal op amp assumptions. In the next video, we're going to kind of skip through a lot of that. But I'm not going to take the time to, for instance, describe what a non-inverting amplifier is, because I'm assuming you already had basic electronics, basic circuit analysis that went over those ideal cases of the basic op amp structures. Basic op amps being inverting, non-inverting, difference, and summing amplifiers. So if you haven't gotten those, it's a good time to probably go back, find a video that covers it. If you look within my videos, the EE111 lecture series, chapter 5 that we go over, that goes over op amps, everything you need to know that. So it's one video. You could take a quick break right now and watch that, and you'd be caught up. But we're going to go over the non-inverting amplifier, and we're going to find the behavior of this, assuming non-ideal effects. But now we're not going to assume everything non-ideal. We're only going to assume that the gain is finite here. So we are going to analyze this, do the math for the non-inverting amplifier, only assuming that A is finite. And so we're still assuming the output resistance is 0. We're still assuming the input resistance is infinite. Let's jump into it. Okay. So this is the non-inverting circuit. So we have the voltage of the positive terminal is this input voltage. From op amp theory, this op amp is going to, assuming very high gain, it's going to try to get this negative terminal to match that voltage here. And, it's got this feedback network, though, this voltage divider R2 over R1, which is breaking up V out. So only a portion of this V out shows up here. And so this op amp has to work extra hard in order to get this node to match this node. that's, I said I'm not going to go over the basics, and I'm kind of quickly going over the basics. So let's start building our equations for this. Ideal analysis, we would just assume that the voltage of the negative terminal was V in, and then we could immediately start finding currents and finding voltages and finding our solution, but we can't quite jump there right now. So in this case, we still can assume that the voltage of the positive terminal is V in because it's connected directly to it, and because we're still assuming that the input resistance is infinite. So we can say the voltage of the positive terminal is V in. Now, what about the voltage at the negative terminal? Well, the voltage of the negative terminal, based on this feedback network, is, you can see it's this little voltage divider. We have V out that's being divided across this network R2 over R1. So one thing to note, this equation is pulled directly from the book, and you might see that and you're like, what is going on there? Everybody comes from a different background. Some people took circuits last year, some people took circuits in 1940. I'm not trying to insult the person who wrote the book, but people use, different equations are the standard equations people use. Ultimately, they're the same equation, but people sometimes use different flavors. I'm going to show you what that flavor comes from. If you did voltage divider the way we taught you how to do it, finding this voltage at this node here would be Vn equals V out times R1 divided by R1 plus R2. Now, one thing we can do, though, is if we take this expression and we multiply it by 1 over R1 times 1 over R1, now our expression becomes V out times 1 divided by 1 plus R2 over R1. So some people, though, when they do circuits, when they do voltage divider, they jump right to this form of the expression. I still personally prefer this one. But I can see the advantage of this flavor. This flavor's only got one R1 and one R2. It's got a divisor in a divisor, though. So that's what I don't like about it. But whatever. They're two separate equations. So all I'm trying to say, I'm just trying to warn you. If you were going through the book would just say, oh, the voltage of the negative terminal is this monstrosity. And you would look at it and you would say, what is going on? 1 over 1 plus the ratio? So what I'm trying to do here is explain it. I'm trying to be a Sherpa that guides you through the Franco book. And if you look at that equation, you're like, where'd that come from? That's just the voltage divider equation. You just use a different version of writing the ratio, the resistor ratio equation. Okay, that's all that is. So I have to provide some value to this class. I can't just be, read the book, do the homework. You're on your own. I could do that, but I won't, because I care about your learning. So we're all in this together. I don't know what that means. We're not in this together. I already passed this class. Yeah, I write the test. You take it. Okay, I shouldn't do this on this video because other people watch this. Okay, I got to maintain my sanity. I got to crack jokes. It's going to happen. It's going to happen. It's like a steam coming out of a kettle. You got to let it out or everything gets too serious and then nobody learns. Okay, so that's the voltage of the negative terminal. We have an equation for the voltage of the negative terminal and the voltage of the positive terminal. And the cool thing is, if we know the voltage of the negative terminal and the voltage of the positive terminal, we can determine this output voltage because we know that V out equals A VD, and VD was VP minus VN, so that's equal to A times VP minus VN. VP is V1, VN, which we already solved for, is that monstrosity. So now we got this expression here. And then, magic of television, we can take this equation here and we can manipulate it into V out over Vn. This is going to give us the gain of our network. It's going to give us the gain of our system. And you see here, they just sort of magic of television this thing into this. And I'm gonna really quickly just show you what they did here to do this. So if we go back to this expression, and again, this is just algebra. You should be able to do it, but I find it helps. If you want to skip through this part of the video, go ahead and skip. If you want to speed me up, go ahead and speed me up. But we're just going to go through this just so it's kind of clear, because there are times when you do the problems, you're going to have to basically go through this process yourself. So we have an equation. It has V out and V in as variables. We need to get a ratio of those to find the gain. So what they're doing here is they're splitting this up into terms. So basically we have V out equals A V in minus A over 1 plus R2 over R1 times V out. We want to get these V out terms on the same side of the equation. So we can say V out times 1 plus A over 1 plus R2 over R1 equals A V in. So now if we want to get this ratio of V out over V in, we have to basically divide both sides of the equation by this and also divide both sides of the equation by V in. So, and that's going to give us V out over V in equals A times 1 over 1 plus A over 1 plus R2 over R1. What am I doing? All right, now did I mess that up? Maybe. Okay. Now, how did they get this? How did they clean this up? So what we can do now is we can take this equation and we can multiply this entire equation. We can multiply this side of the equation by, we're going to multiply this by 1 plus R2 over R1 divided by A divided by 1 plus R2 over R1 divided by A. Okay, if that's a mess. I probably shouldn't have even written that. But what happens when we do that is essentially, so we get, oops, let's just clean this up. Let's put the A up here. So the numerator becomes A times this, which is just this, which is just here. And the denominator becomes this times this, which this and this cancel out to 1, and then this is just this here, which is how we get 1 plus blah, right? Okay, I don't know if that made any sense. I'm trying here. I'm trying. You probably regret the last 2 minutes of your life that were just lost here. So, but that's what happened. The book doesn't show you those steps. The book just says, well, it's intuitive, and maybe it was for everybody who still remembers algebra. But in my opinion, the way you learn things like algebra and calculus and differential equations, the way you learn it is by relearning it over and over and over again. And every time you relearn it, the clearer it gets. So every time we go through these examples, I'm sure doing this manipulation was easy for people in high school, and then it was even easier 2 years ago in math class, and hopefully it's really easy to where 1 minute is enough to get your mind refreshed, and now you're going to do great on the homework. Okay. Let's do an example. So what am I doing? I'm jumping right past it. This is awesome. We now have an equation for the gain of a non-inverting amplifier. Now, ideally, the gain of a non-inverting amplifier is supposed to be this, right? Ideally, it's that. But as a result of a finite gain, a finite little a, as a result of having a non-infinite little a, we actually have this extra term here. So the gain should be 1 plus R2 over R1, but that gain is now attenuated by this ratio, 1 over 1 plus R2 over R1 over A, right? And that is really important for our analysis. So, I mean, this is going to tweak our overall actual result. So let's do an example. Non-inverting circuit, R2 is 20K, R1 is 1K. What is this? Ideally, this would be then non-inverting circuit. Ideal gain would be, let's do that. Okay. So ideal gain would be 1 plus 19K divided by 1K, 20. So ideal gain of this circuit would be 20. But based on our equation here, it's not going to be the ideal gain. It's going to be ideal gain times this little widget over here. So what is that? 1 over 1. It's 20 times 1 over 1 plus, I gotta go back, 1 plus R2 over R1 divided by A. Okay, so let's do this. Let's do this, the case for a gain of little a of 1 of 100. So little a of 100. Gotta find my trusty calculator here. It's buried in the pile. So for a gain of 100, now we're just solving for the gain in this term. So the gain is going to be 20 times 1 over 1 plus 1 plus R2 over R1 is going to be 19 divided by 100. So that's going to be so it's going to be, so this term here is 0.833. That's what I get. So our gain is 16.6. That's not great. We were trying to get a gain of 20 and we got a gain of 16.6 because our little a, our open loop gain of our circuit here was only 100. That's not infinite. That's not infinite. So what's our, so if our input, if our V in was 0.1, our V out is going to be 1.6 volts when it should have been 2. Okay, now let's do it for the case of 10,000. For the case of 10,000, we're going to have 20 times 1 over 1 plus 1 plus 19 divided by 10,000. That's going to be 20 times oops. Twenty times 0.998. So that's a lot better. So that's going to be 19.96. That's a lot better. And so if our input was 0.1 volts, 0.1 times 19.96 is going to be 1.996 volts. So big difference. There's a big difference now between using an amplifier with a gain of 100 and using an amplifier with a gain of 10,000. So 10,000 gets very close to the ideal case of a gain of 20, whereas 100 is not that great. So that concludes our lesson for today. And hopefully you learned something about ideal amplifiers, ideal assumptions, and analysis with non-ideal. And keep in mind, this analysis with a non-ideal was only looking at a finite gain. So this wasn't even taking into account input and output resistance. And this was actually a lot of math just to do a simple example. So it's a warning. It's a warning for what's to come. Just keep in mind, when it gets bad, we find simplifying ways to make it easier, which is what we do in the next, like starting right in the next lecture, we start to make assumptions to make it easier for us to do more complex problems. So thanks for watching. I'll see you next time.